Okay, so yeah, thanks for giving me an opportunity. I'm Jun'ya Kume, a PhD student at the University of Tokyo. And today, I will talk about my recent work with Kohei Kamada and Yusuke Yamada, namely renormalization in gravitational leptogenesis with pseudo-scalar-tensor coupling, which is available on the archive. So, okay. Okay, so this is the contents. So first, I briefly talk about the gravitational leptogenesis. Then I will explain how this gravitational leptogenesis is realized in this model with pseudo-scalar-tensor coupling. Then I will present what we have done in this work. Okay, so let me start. So this gravitational leptogenesis is one way to generate observed baryon symmetry of the universe. And this scenario makes use of the lepton number violation realized in general relativity with standard model particles. As you know, there is right-handed and left-handed asymmetry in the neutrino sector. So you have the gravitational anomaly in the total reactor number current, like this. So this radial is Chern-Pontryagin density, and this capital N represents the difference in the number of species between the right-handed light fermions and left-handed light fermions. So this is just a -3 in standard model. As you can see from this equation, if you have a non-zero wave of our dual, then you have non-zero time derivative of lepton number density. So you can generate lepton symmetry in the primordial universe. And we should note that this non-zero aura dual is naturally realized in axial inflation due to these couplings. And in this work, we are focusing on this phi aura dual coupling. Compared to this phi FF dual case, chiral gravitational waves are directly generated in this model. So we can say that this phi aurora model is a minimal setup for gravitational leptogenesis. Okay, so this is the Lagrangian of this model. And in this work, we'll consider the specific form of F. And this F or this phi aurora coupling is realized by, for example, Green-Schwarz mechanism. Okay, and this pseudo-scalar inflaton phi and matter fields are taken as background, and we assume as standard model particles with 3 right-handed minor neutrinos in the matter sector. And for simplicity, we consider the case where these neutrinos have common mass scale mu. Okay, so this is a setup. So let us consider metric perturbation in the dosic background. So up to the second order, you will obtain the gravity axiom of gravitational wave like this. So this is coming from the phi aura dual. And here, this theta roughly corresponds to the phi dot, h phi dot. And this lambda has a different sign with a different polarization mode. So this leads to the generation of chiral primordial gravitational wave during the inflation. Then after the quantization, you can evaluate the wave of our dual, and this becomes non-zero because of this chiral gravitational wave. And here we take Bunch-Davis-like vacuum, and yeah, mode function is like this. So they're the factor of theta, and we take a function. Okay, So let me talk about the lepton number evaluation in this model. So as I mentioned, we have this anomaly equation. So by integrating this over the inflationary era, you can evaluate the lepton number density at the end of inflation like this. And here we assume that there are no asymmetry at the initial. Okay, so this smooth function has a plane wave asymptotic form like this. So by using this, we can evaluate the value of lepton number. However, this quantity is divergent. So we need to introduce UV-cutoff lambda, and picking the leading divergence, you will find that this lepton number density depends on lambda to 4th. Okay, so then you might have this question. So what is the appropriate choice of this lambda? In order to answer this question, we need to consider anomaly equation more carefully. Okay, so below their mass scale mu, this below this mass scale mu, right-handed neutrinos decouple from the theory. So you have -3 here. However, above mu, the right-handed neutrinos become active. So the right-hand side of this anomaly equation vanishes. So you can say that this mu is an effective cutoff of anomaly equation. In this sense, you can take this mu as lambda here. So you will find the lepton number density depends on mu to 4th like this. So this is the lepton number density produced in this model. Okay, so let me make comment on the baryon symmetry. Before the electroweak symmetry breaking, spiron converts this lepton symmetry into baryon symmetry. But in usual case, this is too small to explain observed value of baryon symmetry. That is because of the smallness of this coupling filter like this. And this smallness is coming from the consistency of this fire audio model. However, if specific reheating occurs, we can explain the observed baryon symmetry within this model. For example, Hubble constant about 10 to 13th GeV, and this random mass about 16th GeV. Then if reheating with temperature about 10 to 7th GeV, and yeah, then you can obtain the baryon symmetry comparable to the observed value. So this is what we have found in previous work. Okay, so this is about the gravitational leptogenesis in this model. But are you satisfied with this evaluation? So yeah, we should consider the subtlety in this evaluation. So this mu is actually a physical scale far below the cutoff scale of EFT. I mean, this mu is far below of this Planck scale. So this is the reason why in the previous work, this mu dependence of lepton number is considered to be valid. However, nevertheless, this lepton number still depends on the cutoff of the momentum integral. In this sense, you can say that this evaluation strongly depends on the way how you regularize the quantum fraction. For example, if you consider dimensional regularization, this n should depend on 1 over epsilon. In this case, the correspondence between this two expression is quite ambiguous, because this epsilon is deviation of number and dimension, but this mu is mass scale of neutrinos. So if you want to remove this ambiguity, we need to perform renormalization of this lepton number. And we should note that this problem was first considered by Fisher and Pava in terms of the effective action of graviton. But in this work, we explicitly perform renormalization with this Bunch-Davis-like mode function. So I think it should be easier. It should be easier to follow our calculation. And for example, the whole UV dependence of our dual is clarified for the first time in our present work. So in order to renormalize, we need to identify the precise UV divergence structure of our dual. And by using Marine-Burns representation, we can rewrite this aura dual in terms of the contour integral like this. And here, the divergences of aura dual can be regarded as the polars of this integral. So after performing the contour integral, we obtain the whole UV divergence structure like this. So not only the false lambda to false, but also there are quadratic and logarithmic divergence we have obtained. And we also performed the adiabatic regularization by using adiabatic vacuum, and it also is correctly reproduces this same UV divergence, so that this fact confirm the correctness of our calculation. And we should note that from this contour integral, we also obtain this finite piece of our dual. And this is closely related to the lepton number evaluation if we assume minimal subtraction as a renormalization condition. Okay, so we have obtained the UV dependence, so let's perform the renormalization. This aura dual physically appears in the equation of motion of phi like this. So by introducing counter terms, you can renormalize this aura dual. And in this work, we have identified the counter terms. So you can absorb these divergences in these coefficients like this. Then you have the renormalized aura dual like this. Okay, so yeah, we obtained the renormalized aura dual. So finally, we have considered the renormalized lepton number density. Assuming that the right-hand side of an anomaly equation can be renormalized in the same way, I mean the radial in the equation of motion, then you have this renormalized anomaly equation. Okay, so then after performing integral, you have then we obtain this renormalized lepton number density in gravitational leptogenesis. And now you can see that the enhancement due to the coupling, due to the dependence on cutoff is removed. So this lepton number density is quite small. And we have found that even if a small entropy production is realized, we can't explain the observed value of this NB over S. So in order to activate the spiral, the reheating should complete before the electrolytic symmetry breaking. So this value gives the upper band for the baryon symmetry of this scenario, but this is still far from this observed value. So if you assume the minimal subtraction in this model, the gravitational leptogenesis fails, unfortunately. Okay, so let me summarize. In this work, we specify the UV divergent structure of all radial in the context of gravitational leptogenesis. And we have also identified the counterterms which can renormalize or radial. Then, if we assume minimal subtraction in the anomaly equation, the lepton number becomes too small to explain Barama symmetry. So our result may cast a doubt for the viability of gravitational leptogenesis in this model. Okay, so that's all.